velocity. Okay, so here you should know what is angular velocity. First, you should know what is angular velocity. Angular velocity is represented by omega. So, what is the meaning of the angular velocity? Suppose a person starts the motion from A and this person is going from A to the B. Okay, so this person is moving on a circular path. Okay, and A to B, and this person covers the angular displacement theta. Okay, angular displacement theta in time interval t. So angular velocity is given by the angular displacement divided by time. Okay, angular displacement divided by time. Now here what will be the linear velocity of the person? Linear velocity when the person will try to move in the straight line. So at point A, if you want to find the direction of the linear velocity, direction, so you will draw a tangent at this point, you will get the direction of the velocity. Here if you want to find the direction of the linear velocity, draw a tangent, you will get. Suppose here if you want the direction of the linear velocity, so what you will do? You will just draw a tangent. So here you will get the direction of the linear velocity. And there is a relation between the linear velocity and angular velocity. V is equal to r omega in case of this circular motion. R is the radius of the circle. Okay, radius of the circle. Okay, now this conductor is rotating in this direction. This conductor is rotating like this. So what will happen? Due to the rotation of the conductor, magnetic flux linked with this conductor will change and EMF will induce in this conductor, and that EMF we will calculate. So how we will calculate? So what about point B? This conductor is rotating. Okay, about point B the conductor is rotating. Okay, so this thing you should know. So I am taking very small element here of this conductor, very small element dx of this conductor. So as this conductor will rotate like this, as this conductor will rotate like this, so this have the velocity perpendicular to the conductor. Okay, perpendicular to the conductor, or you can say you will draw a tangent at this point in this direction, you will get the linear velocity. So this is the linear velocity. And suppose from point B this dx is at a distance of small x. This dx is at a distance of small x, and I have told you the relation between the linear velocity and the angular velocity, x into omega. Okay, instead of r here you will put x. Okay, now in this element dx, in this element dx, a small EMF will be induced. Okay, in this element dx, small EMF will be induced, and that EMF will be given by dE. And what is EMF induced? Minus magnetic field. Okay, length of element, that is dx, and the velocity of this element. Okay, and now we will put this is v dx. Instead of v we will put x into omega. Okay, we will put x into omega. Now we have this dE. Okay, so this dE is the induced EMF in this element dx. For calculating the total EMF induced across the ends of the conductor, we will integrate this equation. Okay, so this is dE is equal to minus v omega x into dx. Okay, we will integrate this. Okay, so from, and there will be the limits of the integration. So limits of the, here x is changing. Okay, here the value of x will be different, here the value of x will be different. At point A the value of x is equal to the length of the conductor. Okay, if you are taking this as a reference point, then from here to here the value of the x will be L. So you will apply the limit here at point B. At point B the x is equal to 0, and at point A the x is equal to length of the conductor. So here you will apply the limit x is equal to 0. Here you will write x is equal to length of the conductor. Now you will integrate this equation. I have told you this v omega will be constant, Magnetic field is constant, angular velocity is constant. So you will take this out of the integration. Okay, now you have this x is equal to 0 to x is equal to L, and this is x dx. Okay, so integration of x dx will be integration of x dx will be x square divided by 2, x square divided by 2, and you will apply the limit also from 0 to L. Okay, and we have minus b omega also. We have minus b omega also. So basically we will get here, you will get the total EMF across the end of the conductor, and uh, actually there was a problem in my internet connection. Okay, so we now, okay, so this is the EMF across the ends of the conductor. Okay, this will be the, so we will use this formula in solving the numericals. Suppose this question, they are saying a wire of length L, a wire of length 2 meter is rotating with an angular velocity of 5 radian per second in a uniform magnetic field of 10 Tesla. Calculate EMF induced across the ends of wire. So very simple. Here length of the wire is given as 2 meter. Angular velocity omega is this 5 radian per second. Okay, and magnetic field is given as 10 Tesla. We have to find the EMF induced across the ends of the wire. So what is the formula? Minus V omega L square divided by 2. Okay, so minus, what is V? Put all the values. This is 10, omega is 5, this is 2 square divided by 2. Okay, so you will get this will become minus 100 volts. This is EMF, so unit of EMF is volts. Okay, unit of EMF is volts. So this is, so we have used this formula, for solving this question. Okay, so now next topic. Now focus here, mutual induction. So now what is the mutual induction? Mutual induction means there will be two coils. Okay, there will be two coils. Here are two coils. Okay, so here are two coils. What will happen if suppose I have closed this switch? So you will see that there will be a deflection here. If I will close this switch, there will be a deflection here. Means when you will close the switch, in this coil there will be the current, and without any physical connection between both the coils. So we will see how this phenomena is taking place. How this phenomena is taking place. Suppose I have closed this switch. I have closed this switch. So this coil 1 is connected with battery. So in this coil there will be current. Suppose I1 is the current, obviously there will be current in this coil. So basically initially the current is 0 and finally there will be some current in this coil. So when you closed this switch, the current will start increasing from 0 to some value, and this is a coil. This is a coil, or you can say this is a solenoid. This is looking like solenoid now. So current carrying solenoid produces the magnetic field. Current carrying solenoid produces the magnetic field, and effect of magnetic field produced by the solenoid 1 will be here also. So basically what will happen when the current will increase in this coil. Okay, when the current will increase in this coil, magnetic field due to this coil here will increase. Due to that, magnetic flux here will increase, and due to increase in magnetic flux, according to the Faraday's law of electromagnetic induction, there will be induced EMF in this coil, and due to induced EMF there will be the current. So that is why there is deflection in the galvanometer in this coil. So you can say here will be the induced current in the coil number second. So basically what can you say? What you can say? That when you are changing current in this coil, there will be the induced current in this coil due to change in the magnetic flux linked with the coil 2. Okay, so I am representing V1 as the magnetic field produced by the coil 1, and phi 2 is the magnetic flux linked with the coil 2. So basically what is happening here, this magnetic field produced by the coil 1 is directly proportional to I1. Why? Because when you will increase this current, magnetic field in this coil will increase. Okay, magnetic field in this coil will increase, or you can say the effect of the magnetic field produced by this coil will increase here also. Okay, so here the magnetic field is increasing. Now what will be the formula of the magnetic flux? Phi is equal to VA cos theta. So you can say magnetic flux is directly proportional to the magnetic field. So here the magnetic field is increasing. So you can say flux in the coil second will increase. Flux in the coil second will increase. So you can say flux in the coil second is directly proportional to the magnetic field V1, and you can say that flux in coil 2 is directly proportional to the current in coil 1, because when the current is increasing in this coil 1, when the current is increasing in this coil 1, the flux is increasing in coil 2. That is why there will be induced current here. Okay. So when you will remove the proportionality sign, you will get a constant, and this constant is known as the coefficient of mutual induction. Coefficient of mutual induction. So basically, the explanation part I have written here. Okay, imagine these two coils you have. Okay, so when current in one coil change, EMF is induced in the neighboring coil. We know that EMF is induced in the neighboring coil. Okay, due to the change in the current in coil 1, flux linked with the coil 2 will change and EMF induced in coil 2. Okay, so all these things you can just write here also. Here you can write. So what is phi 2 here? Phi 2 I am writing here. Here I will write phi 2 is the magnetic flux linked with coil number 2. What is I1? I1 you know. No need to write. Current in coil 1. Okay. V1 you should know. What is V1? V1 is the magnetic field produced by coil. Matthew, tell me coil 1 or coil 2? Matthew?
Coil 1.
Very good. Coil 1. That's good. Okay. So now this coefficient of mutual induction, basically we have now this formula phi 2 is equal to m of I1. Here flux is of coil 2, but the current is of coil 1. So this formula you should know. We will use this formula. Okay. So this coefficient of mutual induction is found by experiment that this coefficient of mutual induction depending upon certain number of things: distance between two coils, okay, orientation, material of these coils. Okay, so basically this coefficient of mutual induction depends upon the separation between the coil, orientation, geometry of the coil. Geometry means what is the shape of the coil, okay, nature of the material of the coil. So basically this thing you should remember. Okay, so now uh, I can write in general flux is equal to mi. Okay, I can write flux is equal to mi. So we know the Faraday law of electromagnetic induction. Actually, here from here I can write phi is equal to mi. Na, phi is equal to mi. So what is Faraday law of electromagnetic induction? E is equal to minus d phi by dt. Faraday law. So you will put phi here. This is dy by dt. And you can put the value of phi here. So you will get mi. So m will be out of the differentiation. Then your EMF induced in the coil will be minus m di by dt. What is di by dt? Change in rate of change in current with time, or you can say rate of change of current. So this will be your another formula. Okay, this will be your another formula. But you should know what is di by dt. So di by dt is rate of change of current. Now we will define the SI unit of this coefficient of mutual induction. So we will rearrange this equation. So we will write E dt divided by di. So accordingly, SI unit of M, I have written M. Okay, I have written M here, minus E dt by di from this equation. We can do easily E dt. So what is the unit of E? Volt. What is the unit of time? Second. What is the unit of current? Amperes. So volt second per ampere is known as Henry. So basically unit of coefficient of mutual induction is Henry. Now if you want to define 1 Henry, so what you will do? You will use this formula. So you will use rate of change of current is equal to 1. You will put this 1 and you will put this 1. Then you will get 1. Okay. So you will put for 1 Henry magnitude of EMF 1 and rate of change of current of 1. Then you will put this in the formula. So basically you will get this, and 1 by 1 is 1 Henry. So basically if rate of change of current of 1 second induced an EMF of 1 volt, then the mutual induction of the coil is 1 Henry. So you can define 1 Henry by using this formula. Okay. Basically what you are doing, you have a this coefficient of mutual induction is this. So you have the formula E is equal to dt by di, this formula. If and minus sign I am not taking because I am talking about the magnitude. So you will put this E value as 1 and di by dt as 1. So you will get 1 Henry. Okay, so 1 Henry is basically when you will change the current by 1 ampere, 1 volt of EMF will be induced in the coil, that will be known as the 1 Henry. Okay. So this is now coefficient of mutual induction. We will discuss. Remember this formula. Phi 2 is equal to coefficient of mutual induction into I1. What is phi 2? Flux linked with coil 2, and I1 current in coil 1. So we will calculate the coefficient of mutual induction for the given figure. So basically these are two solenoids. These are two solenoids. Okay. And these are two coaxial solenoid, means the axis of the solenoid is same. So this is the axis. Axis of both the solenoids are same. So for this white color solenoid, small r1 is the radius, L is the length, and N1 is the number of turns per unit length. Similarly for the yellow color solenoid, okay, I have written here small n, number of turns per unit length, capital N, total number of turns or total number of coils. Okay, so for 1 turn, when you will do 1 turn, then it will become 1 circular coil. Okay, it will become 1 circular coil. So this is your 1 circular coil for any of the solenoid I am talking. Okay, so basically you can say capital N as a number of turns or number of coils, you can say. And I have told you in solenoid the magnetic field due to the solenoid is given by mu naught Ni. I have told you now, mu naught Ni. Mu naught is the absolute permeability and number of turns per unit length. I is the current in the solenoid. So first we will see this. Basically what we want to calculate, we want to calculate this coefficient of mutual induction. Our purpose is this. So basically first we will see this solenoid. So suppose I1 is the current in this solenoid. Okay, I1 is the current in and this formula we know already. Phi 2 is equal to M times of I1. So assume current I1 in coil 1. Okay, Matthew and Naval, are you getting?
Yes, sir.
Naval?
Yes, sir.
We are just using the concepts of solenoid. Okay, and concept of the magnetic flux we will combine and we will get the result. Okay, so now see, assume there is the current I1 in the white color solenoid. Okay, white color solenoid. So in the white color solenoid, when there will be the current, I have told you the solenoid behaves as an electromagnet. So this solenoid will produce the magnetic field. This solenoid will produce the magnetic field. So V1 is the magnetic field produced by the solenoid, given by mu 0 N1 into I1. Okay, because the formula is written here. So we are talking about the solenoid number 1. So it will become mu naught N1 into I. Okay. So V1 is the magnetic field due to solenoid 1. Okay. Magnetic field due to solenoid 1, and I have already told you in the last chapter, I don't know whether you know or don't know, the magnetic field produced by the solenoid, we take the in axial direction. Okay, on the axis we take the magnetic field produced by the solenoid. Okay, so the magnetic field produced by the solenoid have magnetic field produced by the solenoid will be inside the solenoid and in the axial direction. This thing I have told you. So means you can say, due to the current in the white color solenoid, this solenoid produce some magnetic field, and that magnetic field will be inside this white color solenoid. This thing you should remember. Okay, this thing you should remember. So magnetic field due to solenoid 1, this will be inside of solenoid 1 and in axial direction. Okay. Okay, now what I am doing, when I1 is changing, suppose the current is now increasing or decreasing in coil 1. So what happens when the current, suppose the current is decreasing, suppose that this current is decreasing. Okay, you have to relate all the things. Suppose this current is decreasing, so when the current will decrease, magnetic field will decrease, and this magnetic field is inside this white color solenoid, and inside the white color solenoid there is another solenoid also. So basically you can say magnetic field linked with yellow color solenoid will decrease, or you can say, now focus on the yellow color solenoid. We know that the magnetic flux is directly proportional to the magnetic field. Magnetic flux is directly proportional to the magnetic field. Here magnetic flux linked with the coil number 2, that is yellow color coil, will be directly proportional to the magnetic field produced by the coil 1 or solenoid 1. So basically this magnetic field is decreasing, and this magnetic field is directly proportional to current I1. Okay, so we can write this thing here. So basically what will happen, this, so you can say your phi 2 is directly proportional to I1. Flux linked with this yellow color solenoid is depending upon the current. When the current will change, the magnetic flux linked with the coil will change, and whenever the magnetic flux linked with the coil change, EMF induced in the coil. EMF induced in the coil. Now we will focus to calculate the magnetic flux linked with this yellow color coil. So what is the formula of magnetic flux? So what is phi 2? I am writing phi 2. Phi 2 is the magnetic flux linked with solenoid 2, linked with coil of solenoid 2. So basically, first we will calculate the magnetic flux for one coil of this yellow color solenoid. Okay, then we will multiply total number of turns or total number of coil, we will get the total magnetic flux. So now magnetic flux in solenoid 2 is given by, so we know that the magnetic flux is given by VA cos theta. What is theta? Angle between magnetic field vector and area vector. So many time I have told you. Okay, so flux linked with the solenoid 2 is given by magnetic field. What is the magnetic field here? Magnetic field is produced by this solenoid 1. So we will take magnetic field 1. Okay, and area, we will take area of so magnetic field, we will take magnetic field produced by this coil 1, and we are calculating the magnetic flux for this yellow color coil, so we will take the area of this yellow color coil, means you will write A2. Okay, and cos, what will be the value of theta? This is the circular coil. See on this, see this circular coil, this is the circular coil. So this direction of the area vector will be perpendicular here, direction of the area vector will be perpendicular. Okay, this will be the direction of the area vector for the coil, and direction of the magnetic field, direction of the magnetic field is also this, due to the solenoid 1. So angle between the magnetic field and area vector, you can say 0 degree. So here you will put cos 0 degree, and cos 0 degree is 1. So phi 2 will be V1 into A2, and what is A2? A2 will be area of this circular coil, that is pi into R2 square. We will write here pi into R2 square. Okay, now this is the magnetic flux. This is the magnetic flux for this coil, one coil, and this solenoid have n number of coils. Okay, and n2 number of coils. So for total flux, what you will do? You will just multiply here n2, and this is V1, and this is pi, this is R2, and this is square. Okay, now I have told you n2 is given by small n2 into L. You can see here n2, when you will put here n2, so this will become n, and length is same. Okay, so you can put this value here. So phi is equal to n2L. Okay, now V1, what is the value of V1? V1 mu naught n1 I1. So you will put this value, mu naught n1 I1, you will put this value, and this is pi R2 square. Okay, so you can write this phi as n mu naught n1 n2 pi R2 square into L into I1. Okay, now suppose this is your equation number 2, and what was your equation number 1? Phi is equal to mi, phi 2 is equal to mi2, sorry, phi 2 is equal to mi1. Okay, so this is phi 2 total. So phi2 total, that is equal to mi2. Now you will compare the equation 1 and 2. Okay, you will get value of m. You will compare na. So this and this will be cancel out. I will and I will be cancel out. So here coefficient of mutual induction you will get mu 0 n1 n2 pi r2 square into L. This you will get. So coefficient of mutual induction. Okay, you can now note down. Just wait. Okay, note down Matthew and Nawal. Note down. Note down fast. So mutual induction takes place between two coils. When you will change the current in one coil, there will be the induced current in the another coil without any physical contact. This is a person and this person is moving from A to B. So here I have explained you what is the angular velocity.
Can scroll down, sir.
Okay. Nawal completed?
Yes, sir.
Okay. This derivation is important, okay? So and what is this dx here? Dx is the small element of this wire AB. We have done these things many times. Earlier, what I have discussed that your conductor is moving linearly. Here we have discussed the conductor is rotating in the magnetic field.
You can scroll down, sir.
Okay. And write down here what is this dx? Dx is the small element of wire. Okay. Length of a small element of wire. I think you already know this, but I am writing. Add this also. Small length of wire element. So now, okay. and this DE, small DE, is the small EMF induced in a small element of wire. Don't forget what is this DE. D of any, the dx is representing a small displacement, dv is representing a small velocity, dp is representing a small pressure. So like this, oh sorry, so EMF will only be induced in a wire, in a coil, whenever there is a change in the magnetic flux linked with that wire or that coil. So the concept of changing magnetic flux is very, very important. We will use this concept in AC generator also. Completed, Matthew?
Yes, sir.
Okay. Nawal, done?
Yes,
Okay,
sir.
so okay, write down this question. Matthew, when completed, you can tell me, okay?
Yeah, just a second, sir.
No, no problem. I'm just saying when completed, you can say, sir, completed. So that I can.
None, sir.
Okay. I think I should zoom out. Just a minute, just a minute. You can write this also. Now, copy this. Uh,
Done, sir.
Done. Okay, very good. Now you can write this statement.
So can you scroll a bit down?
Scroll up,
Yeah,
scroll down. Okay. Scroll up or down?
down, sir, down. I want to see.
Down. Okay. Completed this thing.
Yeah. Done, sir.
Okay.
Done, sir.
Done. Okay. Now, just wait. Okay. Copy this. These are two coaxial solenoid. One solenoid is like this on the above of this, another solenoid is like this, bounded in the helical form, and both have the same axis. That is why these are coaxial solenoids. You can write here also two long coaxial solenoids. Two long coaxial. Write down this heading first, and after that
So you can scroll down.
Nawal, should I scroll down?
Yes, sir.
So here na, in this chapter, the magnetic flux is very, very, very important. Magnetic flux. Whenever there is a change in magnetic flux, actually each and everything in chapter is happening due to change in magnetic flux. Next thing we will study, that is induction, self inductance, or you can self induction we will discuss. Mutual induction we have covered. We will discuss self induction. That self induction will also based on the change in the magnetic flux. And here I have written this phi 2 suffix t. This means total flux linked with the solenoid. Okay, solenoid number 2. This T means the total.
Done, sir.
Done. Okay, now uh, we have discussed the mutual induction. For mutual induction, two coils. There is a requirement of two coils. Okay. Now for self induction, there is a requirement of one coil. There is a requirement of one coil. What will happen in a self inductance? Now see, focus on your screen properly. Okay, self inductance. Self induction, sorry. Focus on this coil. This is the coil we have. Okay, suppose there is no current here earlier. Nothing is there. This is the coil only we have. This is the coil only we have. Focus on this coil, and this coil is connected to the battery. This coil is connected to the battery. Okay. This coil is connected to the battery. Now see, suppose I have closed this key. What will happen? There will be the current in this coil. There will be the current in this circuit, means there will be the current in this coil, and a current carrying coil produces the magnetic field, and a current carrying coil will produce the magnetic field. So basically what will happen, when you will just close the key, the current will start increasing from 0 to some value. The current will start increasing, so you can say the magnetic field starts increasing in this coil. And we know that magnetic field is directly proportional to the current, and magnetic flux is directly proportional to magnetic field. Okay, so you can say that magnetic flux here will be directly proportional to the current. So basically when current will increase, there will be the change. Current will increase, there will be increase in magnetic flux, and whenever there is a increase or decrease or change in the magnetic flux linked with the coil, EMF will be induced in this coil. Okay, EMF will induced in this coil. So due to that induced EMF, there will be the current in the opposite direction. There will be the induced current in the opposite direction. Okay, so here you can see that self induction. What is the meaning of self induction? Property of coil due to which it opposes any change in the current through itself by inducing an EMF itself. So whenever there is a change in the current in this coil, so this coil will induce an EMF, and due to that EMF there will be the induced current, and that induced current will oppose the given current. Okay, so this is the case when the current is increasing in coil. So this is case number first you can consider. Okay, case number 1. So when the current is increasing in coil, so initially your key is closed, not initially. Initially your key was open, now key closed. So what will happen? Current I means current increase. When the current will increase, current will induce in the coil in opposite direction of the given current. I have told you what is the reason, because of the change in the magnetic flux. Okay, so okay, this is clear, I think. Now when the current will decrease in the coil, suppose right now this switch is closed. Now suddenly you have opened this switch. So what will happen? The current will start decreasing. Current will start decreasing means here the magnetic field in this coil due to this current start decreasing, means the magnetic flux linked with the coil start decreasing. Induced EMF will be there, induced current will be there, but that time the induced current will be in this direction. Okay, in this direction, in the same direction of the given current. So here I have written when current will decrease in coil when key is open. Okay, so when you will open the key, so current will decrease, a current induced in the coil in the same direction. So I have written here also. And there can be one condition also. If the current in the circuit in this coil is constant, if the current is constant, no induced current, because no EMF induced, no change in flux. So basically you have this coil, and so we know that magnetic flux in this coil is directly proportional to the current. So when you will remove this proportionality sign, you will get this L. Okay, and L is the coefficient of self induction. L is the coefficient of self induction. Phi is the flux linked with the coil, I is the current in the coil. So this formula you should know. What is the formula of the mutual induction? Phi is equal to Mi. Okay, phi is equal to Mi. And here L is the self induction, coefficient of self induction. Phi is equal to Li. Okay, now we know the Faraday law. We know the Faraday law. What Faraday law says there? E is equal to, what is E? E will be the induced EMF in this coil. Induced EMF in coil is given by minus d phi by dt. Okay, so here you will put the value of phi dy by dt, and this phi you will put here. So you will get Li. Finally, what you will get? You will get E is equal to minus k L di by dt, and di by dt I have already told you what is di by dt. Change in current with time, or you can say rate of change of current. So this formula you will get, and what is E here? EMF induced. This E is EMF induced in coil. Now SI unit of L is same as that of Henry. Okay, SI unit of L is same as that of Henry. Okay, now basically this formula you should know. Now we will discuss the how to calculate the coefficient of self inductance, coefficient of self induction for a circular coil. I have told you that suppose you have a circular coil, and if there is a current in the circular coil, if there is a current in the circular coil and this circular coil have radius r, this circular coil have radius r, then in that case, and this coil have n number of turns. So I have told you the magnetic field due to this current carrying coil will be mu naught n I by 2r. This is the formula. And direction, for direction you will use right hand thumb rule. So you will get the direction in outward direction. Okay, so this thing you should know. So now here we will just calculate the self induction, coefficient of self induction of a circular coil having n turns. So basically I have already written this formula. So basically you have this coil and this coil have the current I. This coil have the current I in clockwise direction. So due to the current in clockwise direction, there will be the magnetic field, and direction of magnetic field will be given by right hand thumb rule. Just curl your finger along the sense of current. The direction of your thumb will give you direction of magnetic field. So this is going away from me means the magnetic field will be inward. Okay, magnetic field will be inward. So R is the radius of the coil. Okay, so the magnetic field due to this coil having n number of turns is given by mu naught Ni. Okay, this thing is clear. Now, if this current is changing, this magnetic field will change, and due to change in this magnetic field, there will be change in the magnetic flux linked with this coil. And whenever the magnetic flux linked with the coil change, there will be the induced EMF in this coil, and there will be the induced current also. So basically, now we will calculate the magnetic flux linked with this coil. So what is the formula of the magnetic flux? Phi is equal to VA cos theta. So phi is equal to VA cos theta. Okay, so this is the magnetic flux for one turn of the coil. Okay, for one turn of the coil, for n number of turns we will multiply n. So total flux linked with the coil will be nVA cos theta, and theta will be 0. Why theta will be 0? Because theta is the angle between the magnetic field and the area vector. Okay, I have told you many times. So here your area vector will be perpendicular to this coil, and magnetic field is also perpendicular to this coil in inward direction. You can take the area vector in inward direction. So that is why angle theta is equal to 0 degree. Now simply put the value in this formula, you will get the total magnetic flux. Here is n, magnetic field is this. Okay, area, this is the area of circle. So we will put here, this will be cancel out, cos 0 is 1. So total flux you will get this, and we know there is one more equation, phi total flux is given by Li. Okay, this equation we have, phi is equal to Li. So we will compare both the equation and we will get the coefficient of self inductance. Coefficient of self inductance for a circular coil having n number of turns, that is given by mu naught n square pi r by 2. Mu naught n square pi r by 2 we will get. Okay, now self inductance of a solenoid. This is a solenoid having a current I. This is a solenoid having a current I, and I have told you this also. The magnetic field due to this solenoid will be in the axial direction, and this magnetic field will be in the axial direction, and this magnetic field will make the area angle of 0 degree with the area vector. Okay, this is your circular coil, this becomes a circular coil, this is also a circular coil. So direction of the area vector here will be perpendicular, and direction of the magnetic field also will be in this direction. Okay, direction of magnetic field will be also in this direction, and small n and capital N already discussed. Now I am not going to discuss this. So basically, what is the magnetic field? Magnetic field due to the solenoid, mu 0 small n into I, mu 0 small n into I. So what is this? This is the magnetic field due to this solenoid. Okay, this is the magnetic field due to this solenoid. So Due to this magnetic field, there will be the magnetic flux also linked with this solenoid. Magnetic flux is given by phi. Phi is equal to VA cos theta. VA cos theta. And what is V? V is mu 0 Ni. Area of this, actually what we are doing, we are calculating the magnetic flux for only one coil. Okay, for only one coil, what will be the area of this coil? This is a circular coil, so area will be pi r square. And cos, so Matthew, tell me what will be theta here? What will be theta?
0.
0 degree. Very good. We have done this thing many times. So cos 0 is equal to 1. So flux linked with one coil of the solenoid is given by mu 0 and I into pi r square. Okay, so what is this? This is the magnetic flux linked with coil 1 of solenoid. So today I will take your 15 more minutes because you both of you joined late. Okay.
Sir, can I leave a bit early because I have a test tomorrow?
Okay, you have a test. Okay, no problem. So then I will leave on time. Okay, so
Okay.
basically at least this derivation should be completed.
Yeah, all right.
Yeah. So now for total flux, what you will do? Total flux you will multiply capital N with this equation. Okay. So this is mu 0 Ni pi r square. Okay, mu 0 Ni pi r square. And I have told you how to calculate N. N is equal to small n into length of the solenoid. So total flux linked with the solenoid will be given by NL. Instead of this you have placed, and here is mu 0 Ni into pi r square. Okay, now you can write this equation in this form. Mu 0 n square, this is one n, this is another n square, pi r square L into I. And we have one more equation, total flux is equal to self inductance into current. So this is suppose equation number 1, this is suppose equation number 2. So you will compare both equation. Equation 1 and 2. So you will get the coefficient of self inductance as L is equal to this I and I will be cancelled out. Okay, and the phi t will be cancelled out. You will get mu 0 n square, mu 0 n square pi square L, pi r square L. So here we will take the capital R. Okay, I have taken the capital R for the radius. So this formula you will get. Okay, so just note down this, then after that you can leave the class. And Matthew, if you want to go early, then you can take the screenshots also.
It's okay, sir. I can just write this quick.
Okay, if you want to write, then write, and if you want to take the screenshot, then take the screenshot, no problem. So basically this chapter will be finished in 15 minutes in the next class, and in the next class we will start the alternating current. Nawal, are you getting?
Yes, sir.
Basically this is a game of change of magnetic flux. If you have understood how the magnetic flux is changing, or if you know how to write the equations regarding change in magnetic flux, and you have a knowledge of little bit of differentiation, then you can do this chapter very easily. So one topic is left, magnetic, actually 3 topics left. First is inductor. Inductor is basically simple thing, like capacitor there is inductor. And another topic is magnetic energy stored in the inductor, and after that energy density of the inductor. After these three topics, we will start the alternating current. And alternating current, I will start from the concept of the AC generator.
Sir,
So,
can you scroll down?
okay. So please don't miss the next class. I know this time is tough for you. Don't take too much pressure. Okay, relax. Study in a relaxed way. Okay, be honest about your studies. Okay,
Sir, you can scroll down.
yeah. Nawal, if you want to take the screenshot, then you can take.
Yes, sir.
So here you have to understand how the magnetic flux is changing, and accordingly you have to write the equations, and you will apply the Faraday law, then you will get the result finally. In AC is a small, I will say, chapter, not a very. In AC, uh, three types of circuits will be there. Uh, Pure capacitive circuit, sorry, pure resistive, pure capacitive, pure inductive, and after that we will combine. Finish. And there will be LC oscillation and all that. We can complete that chapter in at least 3 lectures.
Sir, you can scroll down.
Okay.
Sir, you can scroll down.
Okay.
So can you scroll down?
Okay. Okay, so this chapter will be finished in at least 15 minutes in the next class. And here now phi suffix t is representing the total flux linked with the solenoid.
Yes, sir.
Done. So basically this L is, we know what is L. I have written here. Phi is equal to coefficient of self-inductance. Okay, guys. So we will meet in the next class.